Cartesian
Product.
product.
Yeah, we haven't gotten to those yet. We're going to do those today.
Well, my question is, it's in 1.2, but the Cartesian product isn't described until section 1.3.
Interesting.
So
Okay.
I was wondering, like, is it possible that they meant that to be the XOR?
Let me pull up the question. So which question is this?
This is section 1.2, question number 4, part D.
That is a Cartesian product for sure, and that's probably just a glitch on the part of the person who wrote the book. So yeah, we'll talk about Cartesian products today, and then yeah, use that as a Cartesian product.
Go ahead and do it as a Cartesian product.
Mm-hmm.
All right.
I've been using this book for several years. You're the first person to have noticed that.
I've noticed a few other things.
I know there's a few others in there, but I've never seen that one before, so cool. All right. So quick note: I'm not going to have office hours on Monday. This coming Monday. Normally they're every day, but I have a dentist appointment 8 o'clock Monday morning. So, so no office hours Monday. The rest of the time is the same as usual. All right. Other questions?
I guess I did have one more question. On those number 4 problems where, it says give examples, and, we're boxing our answer, should we be boxing the entire example? It's kind of like a...
No, you don't have to.
I need more than 2 lines.
The boxing in is more, if you've got half a page of work and then an answer, and then you've got another half a page of work and another answer, right? I want something around so I can just sort of immediately get to, the answer to the first part, answer to the second, and so on. So just something to help, kind of highlight the punchline for the question. So let's go through the homework. It's due on Wednesday, and I'll try to stick with 215 homework being turned in on Wednesday. But let's take a look at it in some detail. And oftentimes on the homework, I will put some clarifying notes. So question. So these are all from homework 1. They're all taken from the textbook, and it comes from sections 1.1, 1.2, 1.3. So let's just eyeball a few of these. So 1.1. So questions 2 and 4. Question 2: list all the elements of the following sets. So what I want you to do is just tell me what the elements of the sets are, and go ahead and circle those or box them or something. So a set of all things of the form 1 over n, where n is a member of this set. All right, the set of all things in the alphabet, this is the regular English alphabet, where alpha precedes F, right? So the letters A through E. The set of all minus K, all things of the form minus K, where K is a positive number. So as someone pointed out, P is the set of positives, and so on and so forth. So your answer for each of these 5 questions is going to be a collection of elements, right? So the elements.
Include the null set for all of those as well?
The null set is not a number of the form 1 over 3, 1 over 4, 1 over 5, or 1 over 6. And the null set is not a member of the alphabet, right? So the null set would be a subset of your answers here, but not actually an element of the set. And that's a subtle but big difference. So yeah, good question. There's a comma instead of a period, so there's another typo. I like this text though. This text is pretty well put together. There may be newer versions of this text too. I haven't looked, but we'll stick with this one. All right. So question 4 says use set builder notation. So remember what set builder notation is. It's the set of all x such that something is true, right? Or the set of all n such that something is true or something is not true, and so on. So think about how you can use, things like this to describe these sets. And there's 4 sets there. And try to explore this a little bit. For example, you could say the set of all x such that x equals 1, 2, 3, 4, 5, 6, or 7. But that's really not very sort of far beyond what this is saying, right? I could say the set of all x such that x is contained in this set. But that's not really, digging into the nature of this set. So try to find a different way to express this. For example, the set of all x in Z such that x is bigger than or equal to 1 and x is less than or equal to 7. So try to do that for all 4 of these questions. All right, and then we go on to section 1.2. And number 4 in there asks you to give examples that illustrate something. So the universe is the integers from 1 through 9, and you got to stick with that universe throughout all 4 parts of this question. Okay? And it says give examples to illustrate the following facts. So we're not proving these things. Okay? We are picking a particular set A from this universe, a particular set B from the universe, and a particular set C from the universe. So I would like you for part A to tell me something like, let A be the set blah, let B be the set blah, let C be the set blah. And then go ahead and state that A is a subset of B. And hopefully you picked A and B so that that's true, right? And then state that B is a subset of C, and then state that A is a subset of C. Right? Now that's not a proof that if you had picked a different A that was a subset of B, right? But it's an illustration of a case where A is a subset of B, B is a subset of C, and A turns out to be a subset of C. Precedes means comes before, so if a letter precedes F, it means it comes before F. So it's A, B, C, D, or E.
It's fair to assume that we're not using both capital and lowercase. One uppercase is, I wrote that assumption on my homework.
What do you mean upper and lower case?
Well, like say if I was writing the alphabet like in kindergarten, you'd
say
big A, little a, big B, little
Oh,
a,
okay.
C, little C.
Yeah, you can just use uppercase A's, A through E. That's fine.
I'm a bit confused on the 1.1 number 2 C. Are we defining K as a negative number, or is it saying K negative and K is the value of K is positive?
This is a little funny notation, but set builder notation, we're saying it's the set of all of these things such that that thing is true. So this is pretty straightforward. It's a set of all numbers in the set of positives such that that number is a factor of 24. So here it's the set of all things negative K, where K is a positive number. So for any positive number K, negative K is a member of your set.
Okay,
So it's kind of taking out the double negative then basically?
Yes.
Okay.
Okay, and then same thing in D. For any n that's equal to one of these things, n squared is a member of your set. Is that good?
I'm still a bit how, because it says list all the elements. From my perspective, they're infinite elements.
Which part are we looking at now?
For on 2C.
2C. Yes, there are an infinite number of elements in there. So, yeah, you can't list them all, but you could list a few of them, and then you could say, dot, 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 or you could write a sentence saying, the set of all blah, or something like that. So, yeah.
It'd be like curly bracket, 1, 2, 3, 4, dot, 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 and curly bracket, deal.
Do something in closer to plain English though. So for most of these we can just list the elements, with commas in between them or something. For this one, just write a sentence or a half a sentence and tell me what the set of all elements would be.
Okay.
And you can embellish it with ... if you want, but don't try to find, the precise correct way to do it mathematically. Do it in a way that would explain it to somebody who didn't know a whole lot about set theory and such. All right, so give examples of, right? So try to pick interesting examples. For example, I could say A is the empty set, and B is the empty set, and C is the empty set, and so yeah, A is a subset of B, B is a subset of C, A is a subset of C. Technically, I would give you credit for that, but the goal is to explore something about subset operations. So try to pick some different sets here that illustrate this fact.
You have to stick with the universe, though, right?
But it has to be a set of elements from the universe. Correct. All right, and then show that A minus B is not always the same as B minus A. So you want to find examples of two sets A and B. They could be different from the A and B up here, right? But tell me what the A and B sets are that you're using here. And then, tell me what A minus B is equal to. Show me that set. And then show me the set B minus A. And then you can simply state, these are not the same. Right? So I want to see a bit of an explanation written out in words here. Don't just throw down a bunch of sets and move on, right? Put a few words on there. It can be, one sentence or something. Question C, if the universe is equal to the union of A and B, and if the intersection of A and B is empty, then A is equal to the universe minus B. So again, pick some sets A and B, show the union and state that that's equal to the universe, show the intersection, state that that's the empty set, and then show what U minus B is and state that that's equal to A. So these are demonstrations. This is like, just showing somebody that these are reasonable things to believe. And then we'll talk about Cartesian products in a bit, but once we do, then you'll take sets A, B, and C, you'll tell me what those sets are, and then you got a lot of stuff to show here. Show me what B intersect C is, right? And say, B intersect C equals blah. And then show me, A cross B intersect C equals blah. And then, maybe put a line under that or something, or circle that as a partial result. And then say, A cross B equals blah, A cross C equals blah, A cross B intersect A cross C equals, this thing intersected with that thing equals blah. And maybe underline that, and then, say those two things that we calculated here and here, they're the same. So you're not quite in front of the stern-faced judge in a court of law, but you're on the bus trying to convince somebody that these things are plausible, that they could be true. So you're just sort of sketching out an argument. All right, and then yeah, go ahead.
So when you're sketching those intersections, you're actually like sketching a picture.
No, just so I could say, okay, so the set B is going to be 1, 3, 5, and the set C is going to be 2, 3, 5. So B intersect C would be the set 3, 5. And A could be the set 1, 2, and so A cross B would be the set 1, 3, 1, 5, 2, 3, 2, 5, or whatever.
We go in, we do the examples for 4 with the assumption that, these are just, given if things line up to such that it's true, kind of thing. Because, there are some examples for B where that can be false.
So B, you want to show an example where this statement is true. In other words, where A minus B is not equal to B minus A.
Okay.
And there are A's and B's where this would be equal to that, right? But try to find a pair of sets A and B where this is not equal to that, and draw that out and write that out. So don't use Venn diagrams for these. You can use that to help you see what's going on, but I want to actually see A equals and show me the elements of set A and set B and so on. All right, question 6 is an interesting one, And so I say, give this a shot. And this is a good one to sort of like talk about and play around with, and then maybe ask questions in class, or kick it around in Discord if you like. Suppose that we have an infinite universe, and A and B are infinite subsets. So 3 questions. If A is an infinite subset, is its complement finite? B is the union of A and B infinite, and C is the intersection of A and B infinite. So think about those and play around with them. It's a good way to explore these notions of complements, unions, and intersections, and see if they persist or break or change when we move to infinite sets. Because usually we think about finite sets. Even if we're working with the integers, we're thinking about, 1, 2, 3, 4, 5. But this forces you to think about infinite subsets, sets containing an infinite number of things. So play around with those. And then question 8, I said, give this a try. And this will not be the question that I grade for points. But it's a good question to experiment with. So this is looking at a collection of sets who are, which represent people at a school. And so 1,600 undergraduate students, 900 who are daytime students, 300 who study math, 1,000 who are graduate students. It asks you questions about these. Like how many evening students are there? Well, that one's not too bad. If there's 1,600 students total and there's 900 daytime students, there should be 7,000 nighttime students or evening students. But try to work with these kind of intuitively and see where it leads you. And we'll make this very specific down the road. We'll start looking at ways that we can answer these questions very precisely, but explore them first, right? And just spend some time looking at those.
I was curious while I was looking at that one, and I think I solved it, but is it, when we're doing those and we're saying, wait, like I've got this set, and I've got this set, and I'm doing the subtraction of sets, in this case, N and G, for example, graduate students and daytime students.
Surprise is where my sticky ones, because we're gonna be on a plane and I don't want my bag to be sticky.
I think we got some people with microphones turned on, so I'm going to say if you're not asking a question or commenting, go ahead and mute your microphone.
And so when we're comparing those sets, we want a number. We write the cardinality of this set minus the cardinality of this set is equal to some number. Is that the appropriate way to show it?
That's the bulk of it, but there's a question of overlaps, and that's really where this whole thing gets interesting. So if there's 100 math students and 100 art students, how many students do you have total? Well, you might have 200, but you might only have 190, because there could be 10 students who are taking both math and art.
Right.
So that's the kind of thing I want you to play around with. All right, I'm going to go ahead and mute everybody's microphone, and then if you want to answer a question or ask a question, go ahead and unmute. And so that's questions 6 and 8, and then section 1.3, I gave you one question, and we're going to talk about Cartesian products, and then it asks you to interpret a Cartesian product where A is a set head-tail, B is a set 1 through 6, and what is the Cartesian product of A and B? How could you interpret it? So that'll make more sense after we talk about products. All right, so let me close all of that out.
There was the one comment about how one of the questions in, I think it's like 1.1, has Cartesian products when it should be a different operation. What was the other operation?
No, that should be a Cartesian product.
Okay.
It's just listed before the book actually talks about Cartesian products. So,
Okay.
yeah. All right, so let's continue on with set theory, and hopefully we will get to story time later today. So I will tell you a story related to set theory and versions of infinity. It's a fun little story. So we talked about power sets on Wednesday, and do you remember what the definition of a power set is?
the set of all possible subsets of a set being power setted.
Exactly. So it's the set of all possible subsets. So the power set is a set, and it's one of the ways we can make a new set from an old set. And you just take all the subsets, throw them inside curly brackets, and you got the power set. Awesome. And we talked about operations on sets, unions, intersections, and so on, and we saw that there was a lot of parallel between what we can do with sets and what we've done in Boolean algebra. And unions look like ors, intersections look like ands, complements look like nots. And that's a good thing to keep in mind. So another notion that is useful is the size of a set. So if A is a set, this is the size of a set, the size of A. But we use a fancy word. We use the word cardinality. And in most cases, cardinality just means the number of things in the set. So if I have a set containing 2 pens and a mouse, the cardinality of that set would be 3, because it's got 1, 2, 3 things. And if I have the set of integers between 1 and 5, the cardinality of that set is 5, because it's got 1, 2, 3, 4, 5 things in it. The funky thing about cardinality, though, is that if A is an infinite set, if it has an infinite number of things in it, cardinality is not infinity. Okay, infinity is not a number. And the number of things in a set, right, if it's finite, it's an integer. It's 1, 2, 3, 1,000, 319, something, right? But if your set is infinite, like the set of all integers, and I say, what's the cardinality of this infinite set? The correct answer is not infinity. The correct answer is not any integer either, right? I can't say there's a million things in there because there's more than a million things. I could say, okay, there's a million, billion, skrillion, gazillion elements in that set. No, there's actually more than that. I could take all the integers from 1 up to that number I just said, and then I could take the negatives of all of those integers. And it's got, at least twice as many elements as the number that I said. So this is going to be an interesting question. What's the cardinality or the size of an infinite set? And we're going to play around with that at the end of class. But for finite sets, this just means the number of things. Yeah, go ahead.
I've heard that it's Aleph null.
Mm-hmm.
We have a term for it called
Yeah.
Aleph null.
So, and I don't think I've drawn this in a while. Something like that. That's not a good Aleph not. But yeah, there's a special symbol that will be used for the cardinality of the set of all integers, and it's called Aleph naught. And it looks much more beautiful if someone who knows how to draw it draws it. It's something like that. But I'm not up on my symbology. But it's definitely not an integer, and it's definitely not the sideways 8 that we call infinity. And we'll see what all that's about in a little bit. All right, so we also, when we were talking about power sets, we made an observation, at least in a few cases, that if you had a set of size n, the power set had size 2 to the n. And so we could write that as saying if A is a finite set, then the number of things in the power set of A is 2 raised to the number of things in A. And that's a really powerful formula. Yay for Cantor, yes. So this was our observation. If we had 3 things, the power set had 8. If we had 2 things, the power set had 4, and so on. If you get a question that says, write the power set of this thing containing 64 things, drop the course, right? Because that's going to be a lot of things to write. All right, go ahead and do an attendance ping. Let me know that you're here. and we'll keep going with set operations. So we talked about negations of sets, complements of sets. We talked about membership tables. I think that was the last thing we did on Wednesday, using a membership table to prove certain equations involving sets. So let me talk about unions and intersections. So we know what a union is, right? You take two things, you just sort of mash them together. And the union is what you get when you combine them. You throw away duplicates, right? So if I have three sets, A, B, and C, I could take the union of A, B, and C. Or, I could take the intersection. And if I have a fourth set, I could, for whatever reason, decide to take the union or the intersection of four sets. Perfectly valid. And since we know that the order in which we take unions don't matter, what can I do? The order doesn't matter. I could take A union B, and that set I could union with C, and that set I could union with D. Or I could take A union B and get a set. I could take C union D and get another set, and then take the union of those two. And it's not going to make any difference. So these operations are commutative. They're immune to reordering. So sometimes what's useful to do is to define something that we can call a family of sets. And this would be a collection of sets, for example, S subscript I, where I equals 0, 1, 2, 3, and so on. And so I might be talking about a whole bunch of sets, but instead of calling them A, B, C, D, E, I'm going to call them S0, S1, S2, S3, and so on. So think of it like an array, right? S bracket 0, S bracket 1. And this could be a finite family. It could be S0 through S9. Or it could be an infinite family. S0, S1, S2, and so on and so forth. All right, so let's play with this notion of a family of sets. So let me define a family of sets. Let the set AI, and I'm going to here let I be a positive integer. Let the set AI be the following. It will be a set of integers starting from I and going up forever. So A sub I will be the set containing I plus 1, I plus 2, I plus 3, and so on. So for example, what would be the elements in the set A1?
Just one.
All positive integers.
It's either just one or it's all positive integers. It turns out to be all positive integers, right? A1 would be the set containing 1, 1 plus 1, 1 plus 2, 1 plus 3, and so on. So that's 1, 2, 3, 4, 5, and so on. What about A2?
We start at 2 and go up again.
Same thing, but starting at 2. A3 would be the set starting at 3. And so on. And so for any positive integer I, I've defined a set AI. Okay, so is A1 infinite or finite?
Infinite.
How about A2?
Also infinite.
Are there any AIs that are not going to be infinite?
No. No.
Okay, good. Right? Now, if infinity was a number, maybe A infinity would be finite, but infinity is not a number. There is no A with an infinity at the bottom of it. But, I could write A 10 gazillion, and that's still got an infinite number of things in it. It starts from 10 gazillion, 10 gazillion plus 1, and so on and so forth, but it's still an infinite set. All right, good. So let's talk about unions. So I could write the following. Union from I equals 1 to 5 AI. And this is a shorthand. This is like that sigma notation that you write in math class. This is saying, let's take a union of a bunch of things. Let's start with I equals 1, and then go to I equals 2, I equals 3, I equals 4, all the way up to and including I equals 5. And instead of summing them, let's take the union. So that's just a shorthand for that. And if I use a variable, this means A1 union A2 union AN minus 1 union AN. Everybody okay with that notation?
Yeah.
These are really just for loops in programming. Right? If I said for I equals 1 to 5, my answer equals my answer union A sub I, right? I'm just doing things inside a for loop. So this is familiar in programming. All right, so let's play around with this. What do I get if I take the union from I equals 1 to n of these sets?
A1.
Somebody said A1. What do you think about that?
Yeah, is it just gonna be 1 to infinity, basically, right?
Yeah, if we look at the first few of these sets, right, the union from 1 to n means, okay, I'm going to start with A1, which is all my positives, and then I'm going to add to that all the positives bigger than 1, right, bigger than or equal to 2, and I'm going to add to that all the positives bigger than or equal to 3, and it doesn't really matter, you know, what my value of n is, because each of these things is a subset of A1. So when I take this union, I'm just going to end up with A1. So yeah, I'll buy that answer. So I'll say union from I equals 1 to n AI equals A1. All right, what about the intersection?
Would this be the set 1 that contains the integer 1?
That's a possibility.
Wait a minute, is this also equal to IA1?
Well, let's try some examples. So suppose n is equal to 1. Yeah, this is just the intersection of A1. That's going to be A1. But what about the intersection I equals 1 to 2?
Is it dependent upon the number of times I intersect? Because when I do say A1 and A2, I'm going to take out all of A2 from A1, but then so I'm left with just the number 1. But then when I go to A3...
Oh, we're not subtracting though. We're doing intersections. You're talking about a complement actually. So intersection says find everything that's in common between the sets.
Yeah, so for that one, you get A2.
So for this one, you get A2.
Yeah. So for the top one, would you get AN then at that point?
So that gives you AN. Right? So if I took the intersection of these three sets, well, you know, I can start with this. I have to throw away the 1 because it's not in here. I have to throw away the 2 because it's not in here. But everything else, 3 on up, is in both of these other sets also. So yeah, this turns out to be AN.
So, sorry, I might be a little confused here.
Go for it.
Let me know if I'm right. So the only reason that n union I equals 1 AI equals A1 is because A1 starts at 1, and therefore it's going to have every single number as the other sets.
Mm-hmm.
Right?
Correct.
Okay,
Yep, you got it.
that makes sense to me.
And the reason the intersection is an is because, you know, whatever an is, there's going to be, you know, the extra stuff you find in these other sets is missing from an. Right? The numbers from 3 through, you know, 3 on up are certainly contained in these other sets, but the 1 and the 2 contained in here are missing from A3. So this intersection will just be an. So what about if we do an infinite union? And this is a bit of a weird notion. What I want you to do here is imagine that you're taking all of these sets, an infinite number of sets, and mashing them all together and throwing away duplicates. What do you think you're going to end up with?
You would just end up with A1, right?
You still end up with A1. Doesn't matter, you know, how many other sets I add into here. Every other set is a subset of A1. So it's just going to throw in some more duplicates I'm going to toss out. So the infinite union of these AIs is still equal to A1. Alright, we'll do one more and then we'll move on. What about the infinite intersection?
I'm not even sure. The null set is where I'm kind of wanting to go with that.
Okay. That's not a bad place to go. Any other ideas?
What we talked about for the LF null. It's not really a number.
Yeah, so Aleph null isn't a number either, and it's not a set. It's really kind of a separate weird thing on its own.
Okay.
Well, since assuming that this infinite approaches at or is like the same magnitude as just a linear infinite, it should be a null set.
Does that sound reasonable?
Yeah, I'm definitely gonna go with the null set.
Yeah, so you're correct. This is the null set. But if we tried to generalize from this formula, we might be tempted to say it's A infinity, right? Well, there is no A infinity. But what's happening is, you know, if I claim that this is not the null set, there's got to be some number in there. So I'll say, okay, the number 17 is going to be in this infinite union. Well, since this includes A18 being intersected, and 17 is not part of A18, 17 can't be in the intersection. And any number that you imagine might be in the intersection, you can find some set AI that doesn't have that number in it. And so you're forced to conclude there can't be anything in this intersection, it must be the empty set. But that's a little surprising.
Like A1 minus infinite, right? Or infinite minus 1.
Yeah, so that's...
Not really a number.
Yeah, so infinite minus 1 is an interesting idea. And that's another thing we're going to come back to today.
I mean, doesn't this to me, like, it kind of like gets into the idea of limits, like, as, you know, as your limit is approaching infinity, you know, our numbers are getting infinitely big, but because of the intersection, we're always like, the only way to get another number or a number that's not is you have to go infinite plus 1 type of thing. Like, so yeah, you always got this like, I've got infinity, well, I've got infinity plus 1.
Right.
In grade school, you know, like, my number is bigger. My infinity is 1 bigger than yours.
Right. Okay, so they said limit, not me. So I'm going to go ahead and put some limits in here. And it's not my fault. Limit as n approaches infinity of the intersection from I equals 1 to n of AI. Looks kind of like the null set. But this is really, really strange behavior. Because in fact, for any integer n, this is an infinite set. Right? It's AI, which is an infinite set. We already said, you know, each of these has an infinite number of things in it. So for any finite number n, this intersection has an infinite number of stuff in it. But when I actually get to where n is infinity, suddenly the answer jumps down to the opposite end of the world, and it's an empty set. So in a calculus course, we would talk about discontinuities and whether this limit actually exists and things like that. So I'll throw this inside parentheses with a question mark.
DMEA.
Yeah. So we'll play around with this at the end of class in a different context. But this is a hint to the fact that sometimes when we move from the finite to the infinite, strange things can happen. So keep that in mind. All right, good.
If you miscalculate in some way like that, I mean, that could be the difference between something running and not running, right?
Oh yeah.
Something
Yeah, definitely. All right. Let me just mention this one since, we're in a computer science class. It's nice to bring this stuff back to something computer science related. Let's look at how we can represent sets in a computer. And remember, a set is an unordered collection of objects, but if we put an artificial ordering on the objects of a set, we can represent them in a computer pretty easily. So let's do the following. Let's say our universe equals the set A, B, C, D, E, F, G, and H. So there's 8 letters in our universe. Okay, I'm going to do something that's not inherently part of the set, but I'm going to put in ordering on these. And I'm going to say this is, elements 1, 2, 3, 4, 5, 6, 7, and 8. And if I have this ordering, I can use a binary number to represent any set. And the way I'm going to do this is I'm going to write a set as an 8-bit number. And if my set contains the letter A, this first bit's going to be a 1. If it doesn't, it's going to be a 0. And if my set contains the letter B, the second bit will be a 1, otherwise a 0, and so on. So I could make the set ABC, and I could represent that with the binary number 11100000. And I could take the set B, C, E, and I could represent that with the binary number A, B, C, D, E. So this is one way we can represent, finite sets using binary. And binary works well inside a computer, so we'll do this sometimes. But if we represent our sets like this, we get some pretty nice processing options. So suppose I want to take the union of 2 sets. So let me call this set X, and let me call this set Y. And let me look at the union. So what would the union of ABC and BCE be? Well, ABCE. So if I were to write that union in binary, I'd have an A, B, C, no D, and E. Right? It would look like that. Well, how is this related to these 2 numbers? Can you think of something from Engineering 270 maybe?
And
it's a logical OR.
or.
If I do a bit-by-bit OR operation, 0 OR 0 is 0, 0 OR 1 is 1, 1 OR 1 is 1, 1 OR 0 is 1. If I take the logical OR of 2 of these binary strings, I end up with a string that corresponds to the union. What do you think I get if I take the logical AND? Just wild guess.
1, 1, 0.
intersection.
Yeah, you get the intersection. So looking at these 2 sets, if I do a logical AND, that's a 0, that's a 1 and a 1, and everything else is going to be a 0. Well, that's the set B, comma, C, and that's the intersection of X with Y. What do you think you get if you take the complement of each bit? Change all your 1s to 0s and 0s to 1s.
You're gonna get A and E, right?
Yeah, you get the complement of the set. Someone put it in chat. Right, so if this is the set X, if I take this number and I take the complement of it in binary, I'm going to get 0, 0, 0, 1, 1, 1, 1, 1. And that's the set D, E, F, G, H. And that's the complement in the universe of this set. So when we looked at membership tables and we looked at identities, we saw that unions look like ors, intersections look like ands, complements look like negation. And here's another case where that works in our favor, because if we translate our sets into binary strings, we can do these Boolean operations and interpret the result as the outcome of doing a logical operation on the sets.
Is there an XOR equivalent, maybe?
So an XOR would be, what would that mean for sets? I think it would mean that it's in one set or the other, but not both. And yeah, an XOR would get you the same result. So what's the string that corresponds to the empty set?
Would it just be all zeros?
It'd be all zeros. And what's the string that corresponds to the universe?
All ones. Yeah.
All ones. You got it. All right, one more question. This is an Engineering 250 question. How many 8-bit strings exist? How many different ways can we write 8 bits?
256.
256, which is 2 to the 8th. Well, any subset of the universe corresponds to an 8-bit string, and any 8-bit string corresponds to a subset of the universe. So if there's 2 to the 8th possible 8-bit strings, there's 2 to the 8th possible subsets. In other words, the power set of the universe contains 2 to the 8th elements. So that's another representation of that fact. Yeah, go ahead.
By subsets, you mean like could be like AB or AC, AH, and so on. Okay.
Yeah, so members of the power set of the universe. So any subset.
Okay.
And it doesn't have to actually be the universe. It could just be some arbitrary set. So this is another way to see that if you have a set X containing n elements, the power set will contain 2 to the n elements. And it's just a consequence of the fact that we could represent subsets as n-bit strings, and there's 2 to the n such strings possible. So set theory and computer science work together really nicely. All right, let's see. I'm going to push off functions for a bit, I think. Let's go ahead and take a 5-minute break, and then we'll come back and we'll do something different and really fun. I'll tell you a story. So let's do a 5-minute break. We'll come back and continue from there.
Attendance ping now?
No, I'll do an attendance ping later.
Alright.
All right. All right, we're back. All right, so story time. It's always nice with this class in particular if at least for part of Friday, we can do something bizarre or weird or extra strange. And so we can do that today. So I'm going to tell you a story. And this is mostly fictitious, but it's based on some true things. So this is a story about a mathematician named David Hilbert, and David Hilbert was a real mathematician. He was very big in the 1800s, early part of the 1900s, and I mean he just looked like a mathematician. So let me find you some images of David Hilbert. Right here you go. Right. I mean this is the classic picture, and I mean come on, right? So who was David Hilbert? David Hilbert was a mathematician, worked in a bunch of different areas, had a number of students, really kind of like shaped mathematics through the 1900s. In part because he posed in 1900 at a conference. He posed a series of questions. They were just called Hilbert's problems, but they were kind of foundational questions in mathematics that he thought people, if they studied these over the next 100 years, would move mathematics in a productive direction, right? And these problems became famous, and people started working on these, and some of these problems were solved, and some of them were not solved. And so if you Google Hilbert's problems, or Hilbert's eighth problem or something like that, you'll find lots of stuff online, lots of good rabbit holes to go down. All right, so that's the end of the true part of the story. All right, so the made-up part is that David Hilbert decides that he's done enough math and he wants to do something different at this part of his life. So he moves to a small town and he buys an old hotel and he renovates it and he opens up for business one night, right? And so this is a little hotel. It's got about 20 rooms to it, and a front desk, and there's a little area people can have breakfast and so on, and he's not expecting to make any money or anything, but it's something to do. It's fun to work with your hands. It's fun to dabble in business sometimes. So he opens his hotel, and much to his surprise, there's a line as far back as he can see of people trying to check into the hotel. So very quickly, all 20 rooms are rented, and everybody else gets turned away. And the next day, the same thing happens. And after about a week of this, he realizes, hey, lots of people want to stay at my hotel, right? He's a world-famous mathematician. So he goes to the bank and he gets a loan, and he goes to Home Depot and he gets some more material, and he builds another set of rooms at his hotel. And so now the hotel has 100 rooms, right? And so he closes temporarily while he's doing this renovation. He opens the hotel, and same thing. Immediately, all 100 rooms sell out. So he does that for a while, and he starts making money, right? Because 100 people staying, and they go and they have coffee and so on and so forth, and he thinks, hey, I should make this hotel really big. So he goes to the bank and he gets a bigger loan, and he hires some people, and he builds a big hotel with 10,000 rooms in it, right? And they open up, and first day, boom, all 10,000 rooms sold out, right? This person had a huge career. He had all these students. The students went on and had other students, and everybody knows Hilbert, or somebody who knows David Hilbert, so really popular hotel. So 10,000 rooms sold out every night. And he's thinking, this is a pretty good deal, I'm making a lot of money per room. Now I got 10,000 rooms totally filled up every night. So this goes on for a while, and eventually, being David Hilbert, who can do fantastic things, eventually he makes the final upgrade to his hotel. And his hotel now contains an infinite number of rooms. And the sign in the front says, welcome to Hilbert's Grand Hotel. And it's grand because it has an infinite number of rooms. So they open up and, line all the way down the street and no problem, right? Plenty of room for everybody. So what does it look like when your hotel has an infinite number of rooms? Well, there's a door next to the check-in counter and it's got a 1 on it. That's room 1. There's a door next to that, it's got a 2. There's a room with a 3. If you go down far enough, you'll find a room with a 100. If you go down far enough, you'll find a room with a 1,000,000 on the door. The main characteristic of having an infinite number of rooms is whatever door you look at, if we call that door n, there's a room next to it with the room number n plus 1. And that's always the case. Doesn't matter what room you look at. Every room has a room to the right. Yet property taxes are a bit of a problem. All right, so this works great, right? Infinite number of rooms, finite number of people on Earth, no problem. Everybody on Earth can show up and they can all get a room. Okay, that's great. So a few months later, it's coming up on Hilbert's birthday, and his friends are saying, we should throw a party for David Hilbert. And they're like, yeah, we can hold it at his hotel. Let's invite a bunch of people. So people start sending out invitations, right? And everybody on the planet ends up getting invited to Hilbert's hotel on this one day for a birthday party. At the same time, there's a lab in Zurich, Switzerland, where physicists were working on the multiverse concept, the idea of multiple parallel universes. And at the exact moment that they were reading the invitation to this birthday party, they had actually opened a portal to an infinite number of universes. And an infinite number of copies of people in that lab heard about this party and teleported to our universe and decided to come to this hotel. So now you have an infinite number of people coming to Hilbert's birthday party, and they're all going to want to stay at the hotel. All right, well, an infinite number of people show up the day of the party, and the front desk clerk starts handing out keys, and when they're done, right, everybody's got a room. Because there were an infinite number of rooms available, there were an infinite number of guests, not a problem, right? But every single room is now filled. Okay, yeah, and an infinite cake. All right, so we have an infinite number of guests, and we have an infinite number of rooms. And each guest is in one room. Every room is full. Every guest is in a room. Nobody has to share rooms. Nobody is without a room, and no room is empty. Got the idea? So it's this perfect correspondence. Infinite number of guests, infinite number of rooms. Everyone's got a room. Okay, everybody got that set up in mind?
Yep.
All right. So now something unfortunate happens. It turns out there was a grad student whose car broke down on the way to Hilbert's Grand Hotel. And their car broke down on the side of the road, and they walked, and, a quarter mile down the road was a gas station, and the mechanic was getting ready to leave for the party, so he, came back and helped him out and so on. He's like, okay, here's what you can do to fix your car. And the mechanic goes off to the party, right? So this grad student is working on his car. A few hours later, gets it fixed, drives into town. This is after everybody's already gotten to the hotel. So the party's in full swing. People are dancing and music's going and all this kind of stuff. And this grad student walks up to the front desk. And he says, I'm here for Hilbert's party. I got an invitation. I had trouble with my car. Sorry I came in late. Is there anywhere that I can stay in the hotel? And the desk clerk, who's very good at their job, says, sure, give me 1 second. And he reaches behind him to a console and he does some things. And he turns back and he hands this graduate student a key and says, here you go. Enjoy your stay. So the first question is, how did the clerk manage to find a room for this late arrival if every room was already full?
He made everybody move to the next room.
Excellent. So he hit a little button, and the button lit up a sign in each guest room that said, pardon the inconvenience, whatever room you're in, please move one door to the right. And the person in room 2 moved to room 3, the person in room 3 moved to 100, the person in room 1 moved to room 2. Everybody still had a room. Every room was full, except room 1 was empty now. That's where the new arrival went. Okay, so think about that. What does that feel like? We had a hotel that was completely filled, but we could still put someone else into a room without having them share.
It's like stuffing that one sock in your duffel bag.
Yes, exactly. You thought it was full, but somehow there's room for one more thing. Right? So that's what happened here. And it's a very easy demonstration that this is possible. Just have each person from room N move to room N plus 1. Everybody can find a new room to move into because every door has a door to the right. So nobody gets kicked out. There's no last person who doesn't have a room to move into. Right? Everybody's still got a room, but somehow we opened up an extra space. And so this is a hint that infinity is a little bit of a weird creature. It's not quite like finite things. If this was finite, even if it had a gazillion rooms in it, right, this wouldn't work. Because there would be a rightmost room, room number 1 gazillion, and that person would have no room to move into. But when you make that final leap to an infinite, suddenly things are fundamentally different. And it's kind of like that infinite intersection where things change when you go from a really big N to an actual infinity.
But aren't there like different sizes of different infinities? Like, can't one infinity technically be bigger than another infinity?
It can actually.
If an appropriate number of guests who are all wearing a unique rational number on their shirt that fills all the irrationals. Wait,
We're coming to this. So I think you're anticipating. You're ahead of me. All right, so we're going to come to this. So if a new guest shows up, right, can find a new room, no problem. Okay, suppose another person had car problems and they show up an hour later and still every room is full. Can you find room for them? Sure, you can do exactly the same trick, right? Everybody moves down one room, no problem. All right. So next situation. Suppose there's a parallel universe with another Hilbert's Hotel, and same thing, an infinite number of people showed up there and filled every room, but there's no party, there's no music, there's no cake, and eventually somebody figures out, hey, we're in the wrong universe. We got to go to that other universe. So this infinite number of people teleport to our universe and all show up at the front desk and say, we would all like a room at your hotel, can you do that? So now we've got an infinite number of new guests to check in. Can that be done?
Yes.
Yeah, because there's still an infinite number of rooms.
There are still an infinite number of rooms. They're all full, though. And if we start moving people down one door at a time, it's going to take an infinite amount of time to get your guests into, right? You're just going to be moving guests forever.
I think Cameron's close, but it's not. Don't move him over 1. Move him over 2.
So almost what I'm thinking, if you move them over 2, you'll open up 2 spaces. But someone posted a version of that in chat. They said move the guest from room N to room 2 times N. And so we're going to have the person in room 1 move to 2, the person in 2 move to 4, the person in 3 move to 6. And so each guest only has to move once, and they only have to move a finite distance down the hall. But after this operation is done, all of the odd-numbered rooms are going to be free. Well, that's an infinite number of rooms. That's where you put your infinite number of new guests.
that'll be really rough on the guest in room 1 million.
It'll be rough on the guest in room 1 million, but hopefully there's a fast escalator, moving walkway.
Well, they just switched universes, so I think they can handle.
Yeah, they can probably handle a fast moving walkway.
If
All
you
right.
want teleportation to get there in the first place, so you just teleport you to.
That's true too. Yeah. So what's our punchline here so far, right? Every room can be full, but if one guest shows up, if two guests shows up, if 100 guests show up, or if an infinite number of guests show up, we can still fit them into the room, into the hotel, right? We can still find a room for them. All right. So now something else happens. Across town, there was another hotel. It was called Blauman's Really Grand Hotel. And Blauman's Really Grand Hotel was grander than Hilbert's Hotel, because the doors in this really grand hotel have room numbers that are real numbers. So here's room 1.1, here's room 2.5, here's room pi, here's room square root of 2, and, any real number, there's a room with that number on the door. And every door has a unique real number as its room number. So it's an infinite number of rooms, and you've got an infinite number of guests in this hotel, and they suddenly realize there's a party going on at Hilbert's. And so all these guests come over to Hilbert's Grand Hotel, and they walk up to the front clerk and they say, hey, we saw you just put an infinite number of people in your hotel. We want to get in the hotel too. And guess what? The clerk shakes his head and says, I'm sorry, but there's not enough room for all of you.
Yeah, because there's more of all the numbers than all the integers, so they can't ever catch up, right?
Effectively, yes. But let's dig into that. Now, if I had done this where all the room numbers were rational numbers, so 2.5, 1.1, 3.33333, 0.142857, and so on, the clerk could still do this. And you could take this bigger infinite number of rooms, you could still fit all these guests into these rooms with integers on the front. But when you get to the real numbers, things are fundamentally different. And even though this is infinite, there's not enough infinite space to fit in this size infinite number of guests.
You just have to figure out mixed mode arithmetic.
Yeah.
Okay. You said that with rational numbers you could fit them. That
With-
doesn't sound right because you still are kind of. You can always make another rational number in between two numbers.
That's correct. That is correct.
It would have to do with ordering, because you can order rationals, but you can't order irrationals.
That's also true. That is a pretty big key. So let me give you a different example. Suppose suppose you had a hotel where the room numbers were 1.0, 1.1, 1.2, 1.9, 2.0, 2.1, 2.2, 2.9, and so on. Right? This is clearly more guests than you have in this hotel. It's 10 times as many, right? But you can pretty clearly still fit the people from this hotel into this hotel by just having each person move to a room, 10 times n, and then fill these people in the gaps in between. So the notion of a bigger infinity is what we're working towards here. And there are bigger infinities, and then there are bigger infinities. And the rationals actually turn out to be the same size infinity as the integers. But the reals turn out to be a fundamentally bigger size than the integers. And we can prove that, and we'll do that maybe at the end of today, but probably another day, because we've only got a few minutes left. But let me play out this story. So how do we talk about these sizes of infinities? Well, we use cardinality. So we say the cardinality of the integers is aleph naught. And it's not a number, it's not an integer, it's not infinity, it's a symbol to mean the size of the set of integers. And if I take the set of integers that are positive, it's exactly the same size. How do we know that? Because if I had, doors with positive numbers, and now I took, integers and put them on the t-shirts of guests, I could still assign each guest to a room, right? If you're positive, go into 2 times your number, and if you're negative, go into 2 times your number plus 1. Put the negatives in the odd numbers and the positives in the evens. So the set of positive integers is the same size as the set of all integers. And the set of, let me just write an E for even numbers, is exactly the same. And the set of prime numbers is exactly the same. And it will turn out the set of rational numbers is exactly the same. But if you'll take my word for it for now, the set of real numbers is something bigger. So the cardinality of the set of reals is bigger than Aleph naught. That we can prove pretty easily. I don't think we have time today, but probably next Friday I can do a proof for that. And it's a really cool proof. It uses something called diagonalization. It's a really powerful but simple technique to show that this is bigger than the set of integers. But I want to explore a different question to wrap things up today. When you start making sets, you start to notice the following. There's finite sets. So the set of letters, the set of pens on my desk, things like that. There's Aleph naught, which is the set of integers, even numbers, primes, multiples of 17, and so on. And there's the real numbers, which has a fundamentally bigger size than the set of integers. And an interesting question is there something in between here? Is there an infinite set that's bigger than the set of integers but smaller than the set of reals?
Isn't that an unsolved mathematical problem?
Well, sort of. So this question is called the continuum hypothesis. Pretty sure I spelled continuum wrong, so I'll just make it extra sloppy. The continuum hypothesis, or CH. And the continuum hypothesis claims that no, there's nothing in between Aleph naught and the size of the reals. In other words, if you start with something that's got the same infinite number of stuff as the integers, and you keep adding more things to it, at first you don't get anything bigger. If you just add one more thing or you just add twice as many things, it's still this size. But if you add enough stuff that it's fundamentally bigger than this, it's at least as big as the reals. That's what the continuum hypothesis claims. Okay, so CH says there's nothing in between here and here. If the continuum hypothesis is false, then there is at least one set with size in between here and here. All right, and we're running out of time, so instead of trying to prove this mathematically, we're going to use democracy. So let's do a vote, and you can raise hands in chat. So let's just do a vote. How many people think, just kind of gut feeling, that the continuum hypothesis is true? And go ahead and do a hands up or a thumbs up in chat. And we got some votes coming in. Not too many votes, so we only got like 3 or 4 votes for that. Okay, how many people think it's false? You're not allowed to abstain, so I'm just going to take everybody else as false. Oh, we definitely got more. 1, 2, 3, 4, 5, 6, 7, 8. All right. So if we did democracy, continuum hypothesis would be false, meaning that there is some set in between here and here. All right, you ready for the answer? Is continuum hypothesis true? If you did not raise your hand, you're not wrong. Is the continuum hypothesis false? If you did not if you raised your hand there, you're not wrong either. It turns out this is not just an unsolvable problem. It's what's called undecidable. So nobody has proven that this is true. Nobody has proven that it is false. But what somebody very clever did prove is that it is impossible to prove that CH is true, and it's also impossible to prove that CH is false. Neither of those can ever be proven. And that statement has been proven to be true. So this is called a formally undecidable proposition. And it's a oddity in our mathematical system, in our system of logic.
Well, realistically, there's really no way to prove that there's not an infinite number of sets between those two, right? I mean, realistically.
Realistically, there could be an infinite number of sets between those. What we know is that no matter what we do, we're never going to find a single set between here, because if we did, that would prove the continuum hypothesis is false, and we've shown that this is not provable. So we know we'll never find a set between here and here, but we'll also never find a proof that no such set exists. And that's potentially really disturbing. This is, saying that we have proven there is a limit to our ingenuity, our creativity, our ability to solve questions in mathematics. It would be like if...
It's not saying that it's unsolvable, it's just saying that we don't possess the tools at this time to solve something like that, right?
It's stronger than that. It's actually saying it is impossible, not just for us, but there is no proof one way or the other.
I guess it kind of depends on your perspective too, because some people will say that math being permanently incomplete is more beautiful than it is scary.
Yeah, and incomplete is an interesting word. So this is an example of incompleteness. There's a proposition that cannot be proven or disproven. And people have tried to improve mathematics, to add some more stuff to it, some more machinery, so that we could prove these undecidable propositions. And guess what? If you add enough stuff to your mathematics to where you could actually prove this, you've also added so much stuff that you've created contradictions. And you'll end up finding paradoxes. And with our system of mathematics, we only have two choices. We can have not enough stuff so that we have undecidable propositions, or we can have too much stuff so that we have paradoxes. And we don't have a sweet spot in between there. And guess what? It's been proven that there is no sweet spot. That's something called Gödel's incompleteness theorem. That's one of the people on the course picture on Canvas. It's Kurt Gödel and Albert Einstein. So mathematics can never be both complete and consistent. It's either incomplete or it has inconsistencies. And this yeah, go ahead.
Is there a way that someone in the future could develop something that could contradict that theory?
Theoretically, no.
No? Okay.
Not with our current understanding of what it means to be a mathematical system and what constitutes proof and so on and so forth. And is that an absolute of the universe, or is it possible there's a different view of mathematics under which we don't find these uncomfortable situations? I don't know. That's a very interesting question, though. All right, so send me an attendance ping, and I will leave you with that for now. If you want to go down some rabbit holes over the weekend, take a look at Kurt Gödel. And he was a logician who came up with this result. It's just called the incompleteness theorem. And he presented it at a conference, and it was a small conference. He was not very well known in the community, and not a lot of people paid attention. But there were a few people in the audience who had read his paper and were like, holy cow, this is like huge. And after his paper was published, it really kind of changed the shape of mathematics and logic and philosophy and religion and sociology and a whole bunch of other things, because there's profound implications of this incompleteness. All right, so that's our weird touch of discrete structures for Friday. Work on the homework. Bring questions on Monday. No office hours Monday morning, but bring questions to class. Monday we'll talk about functions and summations and matrices, and we'll look at something called Russell's paradox. And then we will move into the next unit, which is propositional calculus. So we'll be doing proofs and logic and theorems and things like that. All right. Have a great weekend, everybody. Stay safe. I will see you next time.
Thank you. Have a good weekend.
Thanks.
Have a good weekend.
Thank you.
Can I go to, can I ask a question?